Sorry. Now, we'll wait in silence. Watch all of you sign in. Interesting. We have two people in the back. Let's go, Evan. Now, is it not working? Just reset it. You can grab it and then set it back down. Now, what we're doing today is this. We're going to survey you to see where the answers, what you selected are. Then we're going to do them. Understand this, the assessments from the other day are in the grade book. Now that I know that we can do these as long as these don't go back to you, this should give you, and I'll tell you this nicely, out of the last one you took, that was a good barometer of where you stand in relation to the exam. Overall, we'll say this, and this again, it's one snapshot, so maybe it's those 5 questions that you could have done better or with review or whatever. As it stands now, I picked those 5 as a good random sampling, and the curve normalized very nicely. So there were the same number of 1s out of 5 as there were 5 out of 5s. What you have to recognize is, I would loosely say right now, that out of the 5 points, now I modified the grade to give you a slight curve, but out of the 5 that you would have had on the AP, I'd say if you are expecting a 3 on the exam, you should have received a 3 out of 5 on the last assessment. If you're looking at a 4 and above, it tends to correlate pretty tightly with what you're going to get. Now, it's not impossible for a high 2 to go to a low 4. But at the same time, that depends on you putting in a hell of a lot of work to make that happen. But that gives you a good barometer of where you are now, and we'll see what your scores are individually. You are not to have with you, though, on your desk, your exam, your assessment. So what I need you all to do first is go in right now, give me the answer choice you picked. Oh, take a look at 14. And let me start this one here. Did it come out to you? Okay, so that one went out to you right now. Take a look right now. Input your answer for 14. There's 20 of you there. A, B, C, or D. Go up to the top and click submit when you're done. If you need to see it, here's the answer selection that's there. We're going to judge, see where the answers fell, number 1, because that's going to let you know where you all individually stand. And it gives me a quick item analysis. Looking at what's there, we've got 20 there. Taking a look, by and large, now, the numbers are pretty stratified. I'd say this, the 8 of you that got this, that's terrific. That is terrific. Now, that's a good, this is not a tough question, though, and we'll see why people might have selected A. Looking at what this is, A is a give-up answer. Looking at what we've got here, maybe, because if you did that, you'd go through and say, well, the numerator goes to 0 over 0. That's undefined. That means you've got to do some manipulations. What does that expression, though, mean? Hands up, please, if you can tell me. One of the 8 of you who got that right. What is this? Where did this come from? What is this an application of? Dave?
That's the difference.
This is your derivative formula. Now, looking at that, what does this tell you? That's what the function that you're evaluating is going to be. Because remember, it's f of x plus h minus f of x all over h. So this right here is your f of x. That's your function. So what does this come out as? Choice D. Next one up, let that be the
derivative of the exponent. Wouldn't that be 0? You multiplying 0 by b squared.
What's that?
If you take the derivative of e squared, you have to take the derivative of the exponent and multiply it by e squared. Wouldn't that be 0 times e squared? Which should give you 0.
You're saying to plug a zero,
So
plug a
take
zero.
the derivative of e raised to an exponent. Don't you take the exponent, the derivative of the exponent, and multiply it by the original?
This is asking you to evaluate out the derivative at 2. That's the formula for applying the derivative at 2. Because this would be, it normally would be f of, in this case, 2 plus h minus f of 2, right? That tells you, now, if it was a straight x, that would be e to the x. You see what I'm saying? The difference between them. So this is telling me evaluate out the function at 2. And that's really what the derivative would give you. Now, looking at this next one here, this one gets a little bit fascinating to see. When you see this, you should recognize something immediately. Well, we'll go through, sorry, I'll prompt you for this. We'll stop this one. Can I go back? How do I go back to find the documents? Here we go. 19 was our second question. Going for 19. Did it start? Yeah. 20 of you go through and prompt that quickly. Go through and enter your answers. Looking at what you have. By and large, that's great. You should be looking at concavity. See? Not a round of applause, but let's say maybe a mini thumbs up. I wouldn't spit at you in the hallway. Now, your second derivative, you've got to go through, figure out where it changes. I'm guessing it only had one critical value. Take a look at 18. 18 is fascinating because 18 is what we did last class. So if you got 18 correct, we should be in good shape for understanding what we did previously. It's not sending it out. There we go. So 18 should be coming out to you now. Go through and input your answers for 18. We're in 17, 18 of us. Okay, by and large, that's a good, now we'll see what the miss was for E, but that's good that this many of you got this. The answer comes out to be D. It says, for the function f, we don't know what it is. The derivative is that, and function f contains the point 1 comma 4. What is the approximation for 1.2 using the line of tangent to the graph at 1? Well, first I need to figure out what is the line of tangency to the graph at 1 going to be, and then I'm going to use that to approximate what the function value is at 1.2. So the first thing I need to figure out is what is the slope of, or how would I figure out what the slope is that I'm going to need for this question? You tell me, Evan. Take the derivative at 1, and what's the derivative at 1 going to give you? 3. Then I'm going to use the point 1, 4 to come up with my local linearization, or a line approximating the function at 1 would be y minus 4 is equal to 3 times x minus 1. That's the line of tangency at 1. Let's approximate the function at 1.2 so we can watch how difficult this would be. Y minus 4 is equal to 3 times 1.2 minus 1. So this is y minus 4 is equal to 3 times 0.2. Now 3 times 0.2 is how much? 0.6. So y minus 4 is going to be equal to 0.6. And here I add that. So y, or the output, would be 4.6. Is that what we got? Is that what the choice was for D? Perfect. That's what we did for homework yesterday. Taking a look at the next one, and this will be our last one. Stop documents. 16 was actually very, very easy if you saw something that was there. And I hope for a lot of you 16 was easy, but there's a brute force and brute computation way to determine it as well. Did it not come through?
No.
Saving, starting. Did it come out now? It says resend?
Yeah.
Okay, sorry. It's not always this perfect. Now, we've got 18, 19 of us here, 20 of us. Let's hope we've got good scores on this, and it doesn't look like we did terrific. I'll tell you right now, this is a question that if you're looking to pass this exam, you can't afford to not get right. Here's a question you can, and it's because you stop analyzing what's going on. Ready? Looking at what we have for 19, if the derivative equals the absolute value function, which one could be the graph? Now, let's say I don't recognize something about the derivative function, because there's a key aspect of it we'll deal with in just a second. But let's say I don't get that. How can I figure out what the individual slopes are at various points throughout the graph? The derivative at -2. The derivative at -1. The derivative at, we went too far over, sorry. This graph looks like it starts at about 0. So sorry, I'll go through and evaluate the derivative at 0, my derivative at 1, my derivative at 2, and my derivative at 3. And hopefully by then we can eliminate all the candidates. What is the derivative at 0 going to be? 2. What's the derivative at 1 going to be?
1.
What's the derivative at 2 going to be?
0.
What's the derivative at 3 going to be? Now, and we can continue it out, the derivative at 4 would be, that's enough to go through and figure out what we're talking about. The derivative is not the function value, it's the slope. So looking at that, which one shows a graph? I'll say this, we should be down to 2 candidates. Which 2 candidates should we be down to at this point? It's one of 2 graphs. Which one? It's going to be down to D and E. All of these graphs have exclusively positive slopes. All of these graphs have exclusively positive slopes. Why is it, well, who can tell me why it would be the correct answer? Selection. Why would it be E and not D? 3 of us? 0?
Because I said that the f(x) graph was only positive, so it was always increasing.
This would always be increasing too. This is always, because this is a graph of the derivative. The point can be in the negative quadrant, but have a positive slope. No?
At 2, the slope is still defined.
The slope is defined here. And it's not there. So that's why it's going to be this. Now, there's something that we could have done to narrow this down immediately. What kind of output values am I getting from my derivative? Only positives, which is why A, B, or C are not possible. They all have negative slopes. And trust me, it looks like, what did they bait you with? See here? You misinterpreted that as the function equals. It's not. Looking at what's there, the derivative is never negative. This derivative right here, what's the slope right there and right there? Negative. Okay? So now, what we're going to have you do, put your names at the top. Make sure they're at the top. Actually, pencil touch you down. Hand those up and over to John now. Quickly take out your notes where we left off previously, which, by the way, I didn't. Ready, Cam? You got your 3 seconds of Home Alone right now, okay? So he comes up the stairs and watch. Oh no! Look at that! Oh no! And then he goes, I bet. Is it AP leadership or no? Oh, okay. Sure. Can you talk about how you feel a lot?
We just kind of sit around and talk about how we want better people.
That's terrific.
Seems like a good thought.
It's kind of interesting because we were able to both do AP Calculus and accomplish some good over the Thanksgiving break, which
Isn't that amazing?
we didn't have to do like a whole class on it, we just sort of did it, right?
What was on display?
What? Didn't you guys get the email out? I sent it, I don't know. If you sign up for Infinite, whose parents, let's say this, whose parents got the note? Okay. I sent it out to all of you. I thought I clicked the student box. I don't know if they mailed it out to you all as well, or posted through Infinite Campus somehow. But in any case, I compiled them all. Sent it to you. By and large, did wonderful things. Some of them, yes, but I had them taken out of the envelope, so I don't know who did what. But by and large, you all did very, very well. You did nice things. You helped out. My favorite, some of them, and if I can find it, there's one. In my head, I'm like, you know what's going to be great? You're going to see some old lady crossing the street. and you're gonna help them. Or you're gonna see someone at Wegmans who maybe needs a hand loading a cart, holding a cart where they help their kids out of the, something, right? There was one person, and I don't want, this sounds like a boy thing, but maybe it's not, where it was, I edited someone's comment on Reddit, which apparently is an internet site. I edited someone's comment on Reddit and I helped them fix their computer, like, with my response. And to read it, I was almost laughing until I was crying because I didn't put any constraints on it. I had a stereotype of what I was expecting them to be, especially when you read 15 of them. Like, there was some that made me cry because it was one row. My grandmother has Parkinson's, and she was trying to make mashed potatoes, and it was hard for her to hold and grip the blender or something while she's doing it. And meanwhile, I'm sloppy crying up there going, oh my God. And then I don't realize how many more Christmases I had with my grandmother, and this was really special to me. I'm a mess. And then the next one is, I helped someone on Reddit with build their computer, and I'm like, what? This is not what we're doing. So in any case, by the way, your project, I'm going to send it out. Because you all did so well last time, and I'll put a link up through Google Classroom so you can see it, you're actually going to have another one to go through and do, but I'm going to ask you this. Before what you did, think about what you did right now. That's your X. You're now going to take, and over Christmas, holiday, you're going to do X squared. Wow. I want you to step up your game. Wow. We're not, some of, we'll say that. First try around is modified. We are stepping up to mod A. You're going to have, don't worry, because you're going to have JV and varsity, and you just wait till we get to varsity. Ooh. It's going to be real deal. Now, what we're talking about today is this. We're looking at related rates, and we're going to go through, there's a video even that I can post out for you. I don't know, actually, wait a minute, this might be on here. Is Mr. Myers sitting on here still? See if this plays. I might have to enable sound. Now, take a look at what's here. Looking at these two glasses, we have to, and I haven't seen this previously, so I haven't seen it since last year, I'm sorry, so I don't remember the specific ordering of the question. But when you look at these right here, these two glasses, if I think so, the question says which one contains the most soda. A can of Coke is 12 ounces. How much would you guess is in each? So which one looks like it has more? The one on the left. I think that this works out that they're both the same, but when they're doing this, I want you to notice something. When you do this, what I'd like you to see is the rate of the soda increasing. This height, the rate of change of the height, for both of these will be different if this is correct. Now, I'm going to download this. Won't play it. I don't even know if I have a quick time to play it. Download it, open. Okay. Okay. So now, as you work your way through, we'll see. I think that's going to have to be a second. Oh. Oh, Act 3. There we go. So that one, I guess, contains half as much. So in Act 3. Hang on. What was this? Hang on. Oh, no, I'm sorry. This one, for those two, you can go through and see that this one was half as much as the other one. Yeah, I thought that they were the same. Hang on, let's do this. We'll get to our notes because it's that. All right. What you have to see is, as you pour those amounts though into those containers, it doesn't matter how much is going into them, because what you need to see is, as you pour equal amounts in, whether they're equal or not, it's not, I guess, how much it fills. It's the rate that it's going up the side. So as I pour the same amount in to the thin glass, it's going to rise faster than it would the wider glass. So the rate of change of the height of those two things would be different. Now, what we'll go through and hopefully get this done quickly today, we're going to talk about related rates. And these questions are very, very important because especially they take into account multiple variables. And they look at what's changing when change happens. And again, we talked before about financial applications. As things change, multiple measures could be changing. So like we talked before about, let's say, Apple sales. As the iPhone sales maybe go up, iPad sales might go down. So there's a relationship between the two of them. As one goes up, maybe another goes down. But that figures, all of that together figures into the overall rate of change. Looking at this next one, differentiable functions over time, we can go through any equation with two or more variables that are differentiable functions of time. It can be used to find an equation that relates their corresponding rates of change with respect to time. That's a related rates equation. So it's as this changes, this changes. So something like the Pythagorean theorem, because as one of the legs is going to change, another one would have to get smaller in order to keep the same hypotenuse. We're going to write these out mathematically so we know what we're talking about. First one up, John is growing at a rate of 3 inches a year. So what is changing? So we're saying the change in height with respect to what? Time. So dH over dt is going to be equal to what? Hands up, please, if you can tell me. What is the derivative of height at that specific time going to be? Yeah, 3 inches per year. The change over the time. Next one up. My mutual fund is shrinking by 4 cents a day. What would that look like if we did it out? Adam? Over? Equals? I did it as dollars per day. That's fine. Yes?
I have a related question.
What?
How would you show a second derivative in dy dx1?
It would look, you're saying if this is first, right? The second derivative would be, I think that's the notation. Okay? And everyone, they actually throw that one on there a lot because people then think you take the derivative and square it, and you don't.
Wouldn't that mean that you're taking the respect to x squared?
Yeah, it should be x. I think that's it. I'll go through and Google it while you're doing a question today. The radius of a circle is increasing by 4 feet an hour. So the change in radius with respect to time is that the volume of a cone is decreased by 2 cubic inches a second. So the change in volume at that point would be negative 2 inches in its volume, so inches cubed per second. Now, our guidelines for doing these questions are actually a little bit fun to do because there's some pieces that you've got to go through and constantly be evaluating. But we assign all quantities and variables that are there, including the given, and we've got to go through and figure out what we need to solve for and what we currently have. So we take inventory of what's given in the situation. That's the first step of doing these out. And in all honesty, the toughest part normally is the beginning and or eliminating a variable. We go through and write an equation that's going to represent all of the related rates that are given and what we still need to find. We may need to go through and use the chain rule with respect to time, substitute the known values after differentiation, and solve for the required variable. Now, understand, you're always taking the derivative of this because it's a change in what's going on with respect to time. Not an x, but because, like let's say the first question we're working with, a rubber balloon is being inflated with a gas at a rate of 15 cc's per second. So the amount of gas going in is constant. what is the rate of change of the radius when the volume is 45 cc's. Now, what you have to keep in mind is this. The gas is going in. Think about filling up a balloon. Is it always growing at the same rate? Some of you that work at Wegmans, I still remember, I don't know if they still do it. Wegmans used to have little helium tanks in there. If you ask for a balloon, do you do that there or no? You used to do it? Does it always grow at the same rate? Is the balloon always expanding at the same rate?
No.
No, because as it gets bigger, all of a sudden when you pump in 15 cc's, it's not going to distort it that much. Versus when there's not much there, there's a lot. So the first thing I would go through and do is, and we can't forget, we know everything except the rate of change in the radius when the volume is 45 cc. We're going through right now and trying to figure out, we don't know what the change in the radius is, but that's what I'm looking to find. What I do know is that, well, you take a look at what's there. What quantities do we know that's in there right now? What do we know that's in there right now? Yeah.
What you're changing, or like what you're differentiating is a 15 cc's per second of gas.
There you go. So the change in the volume with respect to time is 15 cc's in gas. The volume is changing. It's increasing by 15 cc's per second. Now there's something else that we know at this point as well. What other information do we currently have? The volume is going to be 45 cc's. So there's the balloon. You're inflating it. Now, what formula do we know? Well, we'll say this. I thought that this was something that they covered in Geo. I'm not 100%. Have you done volume of a, we're going to assume that this is a sphere. Did you do volume of a sphere or not? It might be because I think maybe they've changed it, but in any case, I remember a lot of people actually didn't know it either. The volume of a sphere is this formula here. 4/3 pi r cubed. That gives you the volume of a sphere. Especially if you go into packaging science, you'll discover spheres are the most efficient way to send things and the least convenient way to send things. They minimize surface area. So if you were looking to send to bottom water, the amount that uses the least plastic is a sphere. But logistically, imagine the display at Wegmans, the end cap, if you're literally selling single cans of water that are all circles. Somebody takes one and then all of a sudden it looks like you're walking on.
Are these formulas going to be provided when we start?
I'll say this, the formulas that you're working with should be understood. This one is an extension formula, so I don't know. I may include it. I'll let you know closer to the exam. But the other ones you should know. Looking at this now, I need to figure out what the change in the radius is. One thing that's important for you to know is at this instance, how many variables do I currently have? 2. Pay attention to how many variables you have. If you have 3, you've got to work to get it down to 2. Or if you have 2 unknowns, we'll change it to that. If you have 2 unknowns, we want it down to 1. So I'm looking to solve for the dr, which means I'm going to take the derivative of this equation. If I went through and took the derivative of this equation, what would I? We'll make it easy for you. Oh, Cam, this isn't your level. If I took the derivative of this left side, what would that give me? Because we're trying to find the rate of change, we're trying to solve for dr dt, so we're taking the derivative of this equation. No, the left side. What's the derivative? Who can tell me what we would have on the left-hand side? What's that? No? Close. dV over dt. You have the change in volume over the change in time. The v is a variable. So we treat it as such. It's not a constant. Looking at the next one. Now I'm going to take the derivative of this. 4 pi over 3 is a constant. What would I be left with on the right-hand side? Take a look at what's done. I'm going to take the derivative of the right-hand side now. What would I go through and have if I took the derivative of the right-hand side? Steve? What'd you say? Yes. Times dr dt. Because remember, we're always taking the derivative with respect to time. Now, What are we solving for in this equation, or what are we trying to isolate? dr dt. What do we need to do to make that happen? Well, by the way, before I do that, I can do some substitutions in. Looking at what we have now, we can fill some stuff in right now. Thomas, what can I fill in right now? And what is that equal to? Yeah, whatever. We don't need the units when we do the plug-in, but you're right. It's equal to 15. So the change in volume at this instant is that amount. Now, this formula here references a radius. Do I know what the radius currently is? No. I'm given enough information, though, to solve it. Because we're talking about computing out the rate of change when the volume measures what? Read the question. It's not on my forehead. When the volume is 45. So I need to figure out what the radius would be when the volume is 45. How can I go through in a sphere and figure out what the radius is going to be if the volume is 45? We got one. This is not a Rubik's Cube. We've got three of you. Take a look at what's there. How can you figure out what the radius is going to be if the volume is 45? Evan?
Take the volume equation and plug in 45 will be used to solve the problem.
That's perfect. So what would we do in order to solve this out for R? Hannah, too, what would you do? Yeah. So if you go into your calculators right now, type in 45 divided by, and then in parentheses, the quantity 4 pi over 3. That's going to give you an exact amount. I went through first, and then I did it in 2 steps because I did it without the calculator. The first thing I did was multiply both sides by 3/4, which is the same thing. Now, did you get your answer? Go in right now, please. Whatever you got, type in 33.75 divided by pi, and see, just so we're on the same page, does that match what we got before? Does 33.75 divided by pi come out to be the same thing as your decimal?
Yeah.
Okay. What would we do now from here? Hands up, please, and tell me. We're trying to solve for the radius. So what would we have to go through and do right now? Yeah. Take the cube root of both sides. So, what does that come out to be to 3 places? And 1, let us know what you get. And some change. Notice I use an approximate sign. Now, in general, just so you're aware, don't truncate until the end. Now, my next step is I'm going to go back to this. Why did we do all of this work? Hands up, please, and tell me. What was the point of all of this business on the side? 3 of us, 4? Why did we just handle all of that on the side? Thomas? To get the radius at that instant. Why did we need the radius at that instant? To figure out what the change in radius is going to be, you need to know what the actual radius is over here. So this is going to be this amount here times dr dt. And again, I'm trying to get the dr dt alone. So now, what would I go through and do in order to solve this? I'd go into your calculator, and I would type in 15 divided by, and you go through and compute it out. It's not a mystery what makes us successful.
Grow up.
Yep.
Uh-oh. Too late.
Now, whomever this is, has done an outstanding job. It looks like. Does this match up what we were talking about? Yes or no?
Yeah.
So, let's go back over now. We would compute this out. What is the dr dt going to be equal to? About 245 centimeters per second. That's how much the radius is changing at that instant. So you're finding an instantaneous rate of change in some sort of geometric figure. Is the volume changing? Sure. This is so great because there's so many moving parts in it. It really, really makes you understand, and it hopefully gets you to see that there's a ton of calculus involved. Take a look at the next one on the top of the next page. A pebble is dropped into a pool of water, causing ripples to go out in concentric circles, which means circles that are on top of each other. That's why I went through and found what's there. The radius of the outer ripple is increasing at a constant rate of 1 feet per second. So I'm already going through and looking for info. I'm going to look at this. The radius of the outer ripple is doing that. Next information, probably when the radius is 4 feet, at what rate is the total area changing? So looking at what's there, we know everything except the rate of change when the area is 4 feet. That's what you're looking to find. What shape are we working with? Circle. So what base equation do I need to reference in order to answer out this question? What's the base equation? And I think it was Evan that had asked earlier if the formulas were given. This would not be given. This is expected that you'll know it. What formula do you need in order to answer out this question? Well, what is pi r squared? The area is equal to pi r squared. Now I go over, all right, well that's my base equation that I need. Now I go over and I take inventory of all of the stuff that I know. Who can tell me something that I know based off of the given information? Read for me. I got one person. Who can tell me something? Yep. We're talking about, right now, a radius being 4 feet. That's correct. Who can give me something else? 2 people. Get real. Davey? What's the rate of what? Who can tell me how I would write out what he's trying to say? What's that going to look like? How's that going to look when I write out what he's trying to say? Jake? Yeah. Keep going. What are you going to say? The change in the radius with respect to time, and what is that equal to? 1 what? Make sure, please, that when you do this out, you keep your units the same. By the way, that's one that's interesting. Sometimes they'll throw inches in, and you'll run into that wall. We're looking to go through and solve for. Was there more that we needed to know? We need to know what dA over dt is. We don't know what that is yet. So how can I find the change in area with respect to time at or when the radius is 4 feet? What would we have to do? This one's actually easier than some of the ones we've done so far. Evan W., what would you do here to solve for dA dt, or the change in area with respect to time at this instant? Who can tell me what we would do next? We got one person, 2. Josh?
Looking up for the radius and the area.
Not yet. We don't need to find the area necessarily. We may need it in our later computations. Steve? We're going to take the derivative of the equation. So if we take the derivative of the equation, Jason, what would we have on the left side? And yeah, and then what is that going to equal on the other side? Take the derivative of the other side and to pi r. I don't know if you said the pi or not, but the pi is a constant. So 2 times what's in front. Now it's raised to the first power. And again, it's a chain rule question because you're taking the derivative not with respect to the radius, but with respect to time. You're looking for the rate of change of the radius with respect to time. That's when you're measuring the change over. So now from here, I need to figure out what my dA dt is going to equal. So this right here is what I'm looking to isolate. And we get to this step. So you tell me what's going on next from here. 3 of us, 4. Sam? How would we figure out what the change in area is at this point? You know the formula for it, so figure it out. And? Who can tell me what the change in area with respect to time is going to be? You don't need a calculator. What? What? No. What'd you say it was? Who can tell me what the final one? Plug it in right now. This should be so automatic. Oh, high five the people near you. Noah? What's that?
45 feet square percent.
Why am I getting a different answer than this? Well, yeah. We go through and we make our replacement in. Last time I checked, my radius was 4. This was 1.
I was looking.
Now, we get to this point here, multiply it all together. You can give it out exactly. So what's the rate and change of the area? And yes, the units matter. Remember, area is squared per second, volume is cubed per second.
Area squared.
What?
Yep.
Okay. I want you to read out the last example and draw out. Read and draw out what's there for the last example.
Draw a line.
Now, it says an airplane flying with an altitude of 6 miles on a flight that will take it directly over a radar tracking station. If S represents the distance in miles between the tracking station and the plane, and S is decreasing at a rate of 400 miles an hour when the S is 10, find out what the velocity of the plane is when S is equal to 10. So the first thing, and this one's going to be challenging, so I went through. Now, I sketched this out. Technically, I think when it's flying directly over this, it's getting red here. So what I want to say is, how high up in the air is this?
6 miles.
So I can go through and label that with a 6. Then the next thing I've got to recognize is, doesn't it tell us, yeah, the distance between the plane and the tracking station that it's going to fly over is how much? What did we represent it with? How did we define that distance? S. And now, yeah, we're trying to figure out then what the velocity is, which is down here. And the velocity isn't what that measurement is. It's the change in that measurement with respect to time. Now, we also can fill something else in. Well, let's fill in, I guess, what we know. What is the change in S with respect to time? Negative 400 miles an hour. What is the S value?
10 miles.
10. Now, how can we figure out what the velocity is? And by the way, here, I'll label this in my picture if that helps. How can I figure out what my velocity is going to be? Do you know? Close. That's not going to give you velocity. What is velocity going to be in this case? You're close. You're going to see in 1 second. She said it would be Pythagorean theorem. We will use it, but not right now. Do you know? Change in distance here over change in time. So I'm going to make this my unknown. Now, you're not wrong, because when you do this out, we have to go through and solve this out. But keep in mind, you're going to tell me what is this length going to be. Who can tell me what this length is going to be at this instant? Because you actually have enough information to get the triangle. What's that? No? Yeah, oh, did you say 6, 8, 10? Yeah, so what's this going to be? 8. Okay. So you would do Pythagorean theorem every year. Somebody asks, where did that come from? Pythagorean triple. Now, what formula are we going to be using? This, because we're looking for, as John said, it's the change in the x over the change in the time. The change in that bottom value over change in time will give you what your velocity is, not just the x itself. That gives you the distance. That's why I didn't say what you were, but you're on the right path. Looking at what's here, now I'm going to take the derivative of all of this with respect to time. This one gets a little awkward, but not really. What is the derivative of x squared going to be? 2x dx dt. What's the derivative of this going to be? 0. And then over here, we've got this. Except now, we can fill in all of our stuff. We know the X is gonna be 8. We know the S is 10, the DS is 400. So this is what it's gonna simplify out to. Sorry, I'll get you to your answer right now. So that's what your velocity is at the end. Now, you all have, and I went through and looked today, some of us have not been keeping up with your Math Excel, and that's fine. You can go through and wait till the end. It does you no good. It doesn't mean you're serious about being successful. Now, you're free to go. Hang on one second.
That's the percentage.
He absolutely is. Is it next time? Yep. The 23rd Friday. So you have your
There we go.
diving
What if we're not gonna be there
quiz.
Friday?
What?
What if we're not gonna be there Friday?
Then you're going to have to stop in to get it.
Work?
Sure. You want to take it after?
I don't know.
I don't know either.
It's pretty tempting.
To take it after? You'll be nice and fresh.
Yeah,
Are you kidding me?
Lagged, actually, so who knows?
Jet lag, where are you going?
London.
London? What is this, Friends?
What?